So I have two general pieces of advice, and I think this applies to most math classes, but probably to almost all your classes in general. If you want to do well, do lots of problems. We're not going to give you something that has been so completely out of left field that there's nothing like it you've ever seen before, especially when it comes to multivariable calculus. We've been doing this class, as far as coordination goes, longer than any of the other calculus classes. We have a rich history of problems, many, many deep. And so there's lots and lots of problems. If anything, there's too many problems for you to look at. So make sure, at the very least, see if you can understand today's problems. Go through the recent exams, I would say at least the last year. And make sure you understand all of your quiz prompts. And if you can do all of those, you should be in pretty good shape. Now, there's lots of supplemental problems that come along with those quizzes. Probably there's not enough time to do them all, because on some weeks there's 40 or more problems. But there is enough time for you to look at them and say, what's the first step? Because oftentimes, the hardest thing is to get started. So if you can look at a problem and say, I know what the first step is, then you're in good shape. But if you see a problem that's like, I have no idea how to start, that's when you should think a little bit about. The second point is to take care of your health. Don't pull all-night study sessions leading up to the exam. People have occasionally fallen asleep in exams. It's a very bold move. Doesn't usually work very well. But that also means, get plenty of rest, eat good food, go out and take a walk if you need it. And not just your physical health, your mental health. Don't spend time stressing about the exam or computing massive computations about, well, theoretically, if I got this score, what would I have to get on the rest of the homework assignments? People are amazingly good at computations when it comes to finding their grades. I just wish they were that good when it came to doing the problems. So, all right. With that said, we begin. 15 problems should be done in less than 2 hours. Find the plane which contains the points 2, 4, -1 and 1, 3, -2, and perpendicularly intersects with the plane 3x plus 5y plus 4z equals 487. Now we see a number like 487, it makes us nervous. Well, maybe it's there as misdirection. All right, let's think about this. Whenever we see words like find a plane or find a line, they always mean the same thing. They always say, you better be able to find a point on the plane, or if it is a line, and you better find the vector. Now for the plane, that's the normal vector. If we were talking about finding a line, we would say the direction vector. So every problem that says find a plane or find a line, we always think, okay, I need a point and I need my vector. In our case, our normal vector. Well, the good news is, half of this problem is pretty easy because we have plenty of points to pick from. We actually get 2 points. 2, 4, -1, 1, 3, -2. I'll just pick one. I'll say 2, 4, -1. There's my point. Life is good. Now for the normal vector, that's usually the part you have to think about more. So the normal vector, well, how do you go about finding such a thing? Generally, the rule of thumb is the following. You either hope it's given to you in some way. It's say like the plane is perpendicular to a line, and you say, aha, the direction vector for that line is the normal vector for that line. But if it's not given to you, instead of looking for the normal vector, what you start doing is saying, let's look for 2 vectors which are going to be perpendicular to the normal. Because if I'm after a direction vector, and when I mean a direction vector, I only care about the directional aspect of the vector. If I can find 2 things which are perpendicular to it, that's a win. Because if I have 2 perpendicular things, there's a way to get something which is the right direction. So, what is it? Well, what is it? How do you find, if I have 2 things which are perpendicular, what gives me my right direction? Cross product. Okay, good. Good. Use the cross product, which is denoted by a little cross. All right. I probably should spell product correctly. That will help. There we go. All right. So now we start thinking, okay, so if I want to find 2 vectors which are perpendicular to the normal, I start thinking about the problem. So what does the problem say? Well, I have a given plane, the 3x plus 5y plus 4z equals 487, and then I have these 2 points floating out here in space. I don't need to have a precise picture, I just need to have a picture to help me gain my intuition. And then what I have is I'm looking for the plane which contains those 2 points and perpendicularly intersects this other plane. So that if I somehow were to put these planes right next to each other, I'd see a perpendicular right angle there, coming like when a wall meets the floor. So if I want something that's perpendicular, well, one thing I can look for is a vector that's in the plane. What can we do to make a vector in the plane here? All right. What can we do? We can look at the 2 points because I can make the vector between 2 points. The points themselves are not vectors. So I don't just take the cross product of these 2 points, because you can't take cross products of points. You have to take cross products of vectors. But what I can do is I can look at the vector that goes between these 2 points. That has to be in the plane. So if I look at that vector, I go 2 to 1. That says go down by 1. 4 to 3, go down by 1. And -1 to -2, I go down by 1. Probably should have gone between the other 2 points, but that's okay. All right, down 1, down 1, down 1. Okay, great. Now, that's one vector. Now, the other thing is you probably should clue in on the fact that there's this word perpendicular here. When are 2 planes perpendicular? When the normals are perpendicular. So what happens is I have a normal vector for this red plane. It's coming off. That's the plane I want. Well, it's going to be inside of this other plane. All right. So what I can do is for my second vector, I use the other plane, 3, 5, 4. And now I take the cross, and whatever that vector turns out to be, that's the one I'm after. So we take the cross product, -1 times 4 times I, minus 4i, j times -1 times 3, minus 3j, k times -1 times 5, that's minus 5k. 3 times -1 times k, it's minus 3k, but I was going the other direction, so I add. 5 times -1 times I, minus 5i, but I was going the other direction, so I add. 4 minus 1j, well, again, I was going the other way, so I add, which would give us 1, 1, -2. Now, being paranoid, I always want to check my work as often as I can with something easy. Now, one way to check your work is to repeat the work, but if you're making a mistake, you'll probably make the same mistake again. So it's better here to say, wait a second, I know it has to be perpendicular to where I started. So I do the dot product check. -1 plus -1 plus 2, that's 0. 3 plus 5 minus 8, that's 0. That's good. Life is good. So here, this is the normal vector. Now I have my point, and I have my normal vector. So my coefficients for my plane are 1, 1, minus 2, x plus y minus 2z. To find the other side, plug in 2 and 4 and -1. So 2 plus 6 plus 2 more. Sorry, 2 plus 4 makes 6, plus 2 more makes 8. So the plane, x plus y minus 2z equals 8. All right. Number 2. So you're flying a small X-wing craft to do a surveillance mission around an asteroid. In order to avoid detection by a nearby Imperial cruiser, you must always keep the asteroid at the midpoint between your ship and the cruiser. So maybe we should draw a picture. All right, so what's our picture? Well, we have to imagine we can draw. So here's our little bit of an X-wing craft. It's very small, but here's us. Okay, here's our little asteroid. All right, so I'll say X-wing. Label it so we can actually understand it. Asteroid. And then we have this big Imperial cruiser. All right, now you're probably thinking, what is all that you're talking about? What's an Imperial cruiser? And I am not doing a very good job of drawing an Imperial cruiser. You have to imagine that I was a better artist. It looks like some sort of weird pie right now. Okay, but here's our cruiser. All right, so there's our basic setup. So there's our thing. So we always have to make sure that the asteroid is in between, so we're avoiding detection. So what do we have? Oh, I didn't update this. This is not a small moon. That's no moon. It's an asteroid. Okay. So asteroid, sorry. Given that the asteroid is located at 1, 3, negative 2, so I know where this point is, 1, 3, negative 2, and that the path of the cruiser for time 0 to 1 is given by a parametric curve. So this is the cruiser for time 0 to 1. The question is, where does the x-wing, what path does it need to follow? So we want to produce a parametric path for the x-wing that satisfies a certain condition. So what can we do? Well, what's the clue? What's the key word in this problem? Key word is midpoint. So oftentimes if you read a word problem, what you want to do is sort of start to strip away unimportant stuff. And most of this is unimportant. You can start saying, okay, look, certainly anything that has numbers and variables involved, got to pay attention to that. But then we're looking for other words that actually have meaning for us. So in our case, midpoint, that's actually something which means something in our multivariable calculus setting. So what does that say? We know that we have this point, t squared plus 1, t cubed minus t minus 1, and 4 minus c to the t. We're looking for the x-wing. I'll call it x of t, y of t, z of t. We don't know what those are yet. That's what we're trying to figure out. And what we need to do is we need to say, well, if I take the midpoint of these 2 points, I've got to be at the asteroid. So how do we take midpoint? Well, the answer is we add the coordinates and divide by 2. So we add the x coordinates and divide by 2, add the y coordinates divided by 2, and add the z coordinates and divide by 2. So we go through and do that computation. So we're going to have x of t plus t squared plus 1 divided by 2, y of t plus t cubed minus t minus 1. And then we're going to divide that by 2. And then we're going to have z of t plus 4 minus e to the t and divide that by 2. And that has to match 1, 3, negative 2, which really gives us an equation for each entry. The first entry is 1, the second is 3, the last is negative 2. And once we have that, we're basically done. All that's left to do is rearrange. So in the first case, if I multiply by 2, then I subtract off, I'd say that x of t needs to be 2 minus t squared plus 1. Y of t, well, I would double, so that would be 6 minus t cubed minus t minus 1. And z of t, well, okay, double, negative 4 minus 4 minus e to the t. Now, if we wanted to, we could simplify. And we would simplify if the instructions told us to. But right now, this hasn't told us to simplify. And therefore, if we want, we found our path. That's our answer. And we're done. Good. All right. I should have practiced drawing an imperial cruiser before I started. All right, mental note. Next time I have an imperial cruiser problem. All right. Well, now that we've warmed up, we can start doing some fun stuff. So find the cumulative arc length function s of t with initial starting point at t equals 0 for the curve r of t equals e to the t squared I plus 1/6 t to the 6j plus 2t squared minus 4 e to the t squared over 2k. Well, this should be interesting. Let's see where we end up. All right. Now, one of the things is you should be ready for us to present a parametric curve in multiple different ways. And if you're not comfortable with the way it's given, change it to the way you like. So oftentimes we've written this in a slightly different format. So e to the t squared, comma, 1/6 t to the 6, comma, 2t squared minus 4 e to the t squared over 2. These are the same thing. It's just a different expression. So make sure you're comfortable with whatever format we give, and you can move it into one that works for you. So what's arc length? In particular, what's cumulative arc length? So cumulative arc length says, what's the total amount of distance you travel? So you integrate from 0 up to time t of the magnitude of your r prime of tau d tau. So if you go back and say, well, what is that doing? Well, your r prime is your velocity, and when you find the magnitude, well, you end up with this speed. So if you're looking at the cumulative distance function, it's the integration of speed over some time period, in particular from when you start. Now, you might ask the question, how did I know to start at 0? And the answer was, the problem told me to start at 0, because it says starting at t equals 0. Okay. So what's our next step? Yeah, we need to find the magnitude of r prime. So probably we should find r prime. All right, that seems reasonable. So we have that r prime of t, go through, derivative of e to the t squared, 2t e to the t squared, derivative of 1/6 t to the 6, t to the 5th. All right, derivative of 2t squared minus 4 e to the t squared over 2. Well, time to product roll that. Derivative of the first term, that would be 4t. Leave the second term alone, e to the t squared over 2. And then we're going to add to that the first term, 2t squared minus 4, times the derivative of the second term. Well, what's the derivative of e to the t squared over 2? E to the t squared over 2 times t, because we have to do the chain rule. All right. Now, if we stare at this for a little bit, we say, wait a second, something nice is happening here. You see a 4t e to the t squared over 2. There's a minus 4t e to the t squared over 2, which means that those terms cancel. So that the second term here, this is simplified to become 2t cubed e to the t squared over 2. All right. So now, since we have r prime, do the magnitude of r prime. So that's going to be the square root of square of the first term, 4t squared e to the 2t squared plus t to the 10th, square that term, plus square this term, 4t to the 6 e to the t squared, because I'm just squaring each part, 4 and then t to the 6. And then when I square this, multiply the exponent by 2. Now, if you see an arc length problem, you're probably going to have to tackle the integral, which means that we're going to have an integral which involves the square root. How do we handle integrals which involve square roots? Well, we get rid of them by, the way we handle such integrals is we get rid of the square roots, which means we're hoping that the inside should be a square. And so now what you should think of is I really want the inside to be a square thing. And what we mean by that is we really want it to look like a squared plus 2ab plus b squared. So we have to start thinking. Now, they may not necessarily have it be the case that this is a and this is b. So you sort of have to think, okay, what makes sense to be in the middle? And t to the 10th definitely doesn't make sense to be in the middle. It's not feeling very 2ab-like. But if you're looking at it some more, we say, okay, it seems like this should be a squared, this should probably be b squared, and this maybe should be 2ab, maybe. The reason I think that would be my guess is I just look at the forms. This has an e to the 2t squared, and this has an e to the t squared. And if I square e to the t squared, I would get that form. So that's good, because in the middle I don't have a square attached. It's just a or it's just b. And this has nothing attached. So if I rewrite this, what would this be? Well, the first term, I can rewrite this as 2t e to the t squared squared. This term, well, let's write the last term. There's a t to the 5th squared. And now let's check out if it works. So the question is 2 times 2t e to the t squared times t to the 5th. Does that match 4t to the 6 e to the t squared? And the answer? Yes. Ah, wow, cool. It's like they planned it to happen, because they planned it to happen. I know, because I'm the one who planned it. All right. So the inside is a nice perfect square. Okay, good. Which means the square root of a square, this becomes simply 2t e to the t squared plus t to the 5th. So now, that's sort of computation on the side. Let's do our cumulative distance function. We've done the hard part. Integral 0 to t. And now, this is our function. So it's going to be 2 tau e to the tau squared plus tau to the 5th d tau. The reason, by the way, I'm using the symbol tau is because I'm already using t to represent the upper bound. I don't want to use t in two different contexts. That can be confusing. All right, well, this should not take too long. What's the integral of 2 tau e to the tau squared? E to the tau squared. Integral of tau to the 5th? 1/6 tau to the 6. You might say, hey, that seems really familiar. It happens a lot in these types of problems when you get a lot of the completing the square type things going on. Integrate from 0 to t. And so that leaves us with e to the t squared plus 1/6 t to the 6. All right, is that correct? It's not correct. What did I forget to do? No, it's not a plus c. It's a definite integral. I forgot to plug in 0. You know, so often when we plug in 0, it goes to 0. Sometimes we don't even think about doing it. But here, it's e to the 0, which is actually 1. Okay, so we do have that. 0 to the 6 is 0. So this is the answer for part A. So here's part A, the cumulative distance function. Good. Now, if you're getting nervous about this algebra, I will say I have seen the exam. And when I do the review prompts, I try to make them sort of more interesting algebraically, so that when you see the exam, it's like, wow, I'm glad at least it wasn't as bad as the review problem. So I think it's better than the other way around. So, all right. So there's part A. Then there's part B. Find S of 3 minus S of 2. Well, for this one, you don't actually even have to do very much. You just say, okay, S of 3 minus S of 2. Well, you just plug in 3. And so you get e to the 9 plus 1/6 times 3 to the 6. And you don't even have to know that 3 to the 6 is 729. We're not even going to ask you to do that. You just leave it like that. Okay, and then minus 1. So you just plug in 3, subtract. Now you plug in 2. That's e to the 4 plus 1/6 times 2 to the 6. And again, you don't have to know that 2 to the 6 is 64. Just leave it like that. And then minus 1. If you wanted to, you could do some minor simplifications. For example, you can cancel the minus 1s. But that's not required unless it's told that you need to do that. So what's the point here? Well, there's really 3 to the 6 minus 2 to the 6, over 6. All right. There's our answer for the difference. So that's the first part. But then there's this and. Give an explanation of the value. So what do we have? Well, S of 3, that's the total distance we've traveled from time 0 to 3. Because that's what the cumulative distance function is telling us. How far do you go? So this is total distance from 0 to 3. What about S of 2? What is that? Right, S of 2, similar, but that says 0 to 2. And if I take their difference, what do I end up with? So I take 0 to 3, take out 0 to 2. What is this? This is the total distance from 2 to 3. So once you have the cumulative distance function, now you can answer any question about how far have you traveled along the curve? You don't have to do any more recomputations. You just say, okay, when do I evaluate? And that'll get me my right answer. All right. Any questions on this one? Good. Moving on. So, this problem deals with a solid formed by 1 over root 3r is less than or equal to z is less than or equal to 1 plus the square root of 3 minus r squared. And part A says, find the volume of this solid. And then it gives you a bunch of volumes equations. But before we use the volume equations, we probably should try to understand the solid. Now, this is telling us something about a solid, which means that here, when we see the word solid, we know we're in 3 dimensions. So we're in a 3-dimensional setting. And moreover, we also have another clue about what's going on. When we see r and z mixed together, what do we think? Yeah. So this is cylindrical coordinates. So what's happened is they've given our equation here, our relationship, in terms of cylindrical coordinates. So what we think is, all right, let's try to understand things in cylindrical coordinates. Now, one of the things that you'll notice here is there's no theta. So no theta, what that implies is you get rotational symmetry. Because you'll get the same thing for every single theta that you'll encounter. So you can take advantage of that and say, all right, let me look here in what I can call the RZ plane. And we're going to draw what's going on. So we have 2 things going on. We have 1 over root 3r equals z. And what would that look like? Just in the RZ plane. It's a line. And it's a little bit of a shallow line because 1 over root 3 is smaller than 1. It's coming out. All right. And then we have this other curve. That's z equals 1 plus the square root 3 minus r squared. Now, what does that look like? It may not be most obvious, but we can rewrite it. Z minus 1 squared, because I'm going to subtract 1 and then square, would be 3 minus r squared, or r squared plus z minus 1 squared equals 3. So what if you saw that? It's a circle. It's a circle where you move, the center is at r equals 0 and z equals 1. And what's the radius? The radius would be square root of 3. So, by great coincidence, if you were happening to go out here to root 3, you would then end up going up by 1, so they intersect, and you see the circle coming up. All right. So that's what's happening here in the RZ plane. Now what you do is you spin it around. So what do we see? Well, in 3 dimensions, what will end up happening is we're going to see this sort of shallow cone here at the bottom. This will spin to form a cone. And then it's topped by sort of a half sphere. So that's what we see. So now that we understand the solid, we can start answering questions about the volume. All right, do I need to know the volume of a cylinder? No. Do I need a volume of a cone? Yes. So volume of cone, so that's the downstairs part. So for the cone, we're going to get 1/3 pi. Then the radius would be this length, which is root 3 squared. And then the height is that length, which is 1. So that turns out to be pi. All right. Do we need the volume of a sphere? Yeah, because that's the top half. And the top half is actually 1/2 of a sphere, because it's a half sphere. So we're going to have 1/2 of 4/3 pi. What's our radius? Radius is square root of 3, then cubed. So Square root of 3 cubed is the same as square root of 3 times square root of 3 times square root of 3, also known as 3 square root of 3. The 3's can cancel, and 2 can go into 4. So what we end up with is 2 square root of 3 times pi. And so now, putting this together, we can say that the total volume of our shape is equal to pi plus 2 square root of 3 times pi. All right. So learn to think geometrically and to know how to use the coordinate systems, because that's one of the things we talked about, is how do we use these different coordinate systems. Now that's part A. The problem, it's not done with us. Not yet. It wants more. All right. Rewrite the bounding surfaces as equations in terms of spherical coordinate systems. Well, some of these aren't so bad. So for instance, we see this cone here, this line. And remember that when we talk about spherical coordinate systems, we have these three things. We have phi, theta, and we have rho, which looks an awful lot like p. The good news is that theta does the exact same thing that it did before. So in other words, the theta for cylindrical coordinates is always the exact same as the theta for spherical coordinates, which means, since we don't see a theta showing up, we probably won't see a theta showing up here either. All right. So how about phi? Well, phi, that measures the angle you come off the positive z-axis. And so whenever you see a cone that has a tip at the origin, you can say, okay, well, what you have is you have some angle here, phi. So the only thing we have to figure out is what's the right angle. So we know we can make a little triangle here. Now this has root 3 and 1. And if we know our trig, which maybe we should know a little bit, do we recognize this type of triangle? Yeah, it's a 30, 60, 90, which means that this angle here is the 30 degrees. But of course, we do calculus, so we call it the pi 6. This angle is the 60 degrees, or pi thirds. So what is phi? Well, phi, if you think about it, well, I don't go all the way down to pi halves. That would be down here. I would come up short. So it turns out that phi is this complementary angle to pi 6. So we get that this becomes pi thirds. So the bounding surface, we have that z equals 1 over root 3r becomes phi equals pi thirds. All right, that's one of the two. What about the other one? Well, for the other one, how do we write it? Well, let's just start with an equation, because it doesn't say we have to solve for anything. So we start with our equation, and we already have this equation, r squared plus z minus 1 squared equals 3. And now we say, all right, what are some relationships, or in other words, maybe better yet, what are some ways to go from one coordinate system to a different coordinate system? Now, there's a handful of formulas that you should know, and the ones that you should know really well are r squared equals x squared plus y squared. Rho squared, that's x squared plus y squared plus z squared. X equals r cosine theta. Y equals r sine theta. And the last two are the following. R equals rho sine phi, and z equals rho cosine phi. These are the basic formulas to go back and forth between the different coordinate systems. And if you have these formulas, you'll be able to jump back and forth between any coordinate systems you need to do. So in our case here, we have the last two formulas. You save the best for last. So r equals rho sine phi, z equals rho cosine phi. So we can just simply plug those in. You get rho sine phi squared plus rho cosine phi minus 1 squared equals 3. And we can actually stop there, because it just said rewrite the bounding surface as an equation. Well, there's an equation. That's all in terms of our new coordinate system. And so we'd be done. Now you could, if you were being really mean to yourself, go further, but we don't want to be mean to ourselves. That's not the calculus way. we love ourselves. That's the calculus way. All right. Let's see. A slightly different problem. A particle is traveling along a curve which is parametrized in cylindrical coordinates by r equals t squared, theta equals t, and z equals 26 minus 6t to the 6. So you got to be careful here, because notice what's happening. We have a parametrized curve. And when we talk about a parametrized curve, that just means, oh, I can tell you my location at any given time. We're used to having to do it in terms of x, y, and z. But there's nothing that says we can't describe our location in a different way. So it's saying, okay, now we're describing things not in terms of x, y, and z, but in terms of r, theta, and z. So at a particular time t equals 1, the particle leaves the curve and moves in a straight line. So in other words, on its tangent line. Where will the particle collide with the xy plane if it continues along the tangent line? So what's happening? I have this curve doing something. So it's moving through space somehow, I don't know. And at a particular time, this particle is going to jump off the curve, and then it's just going to move forward along its tangent line until eventually it's going to hit the xy plane. What happens there? I don't know. Maybe it's going to collide with something, or maybe not, but that's up to the particle. We'll let the particle do what the particle wants to do. All right. So what are we going to do? Well, we really need to find the tangent line, but we have a problem. Not that we don't know how to find tangent lines. We do know how to find tangent lines, but how do we know how to find tangent lines? When we have like x, y, z, we don't have that. So what's our solution? We make it. So if it's not in the form that we need, can we change it to the form that we need? And the answer is yes. So remember, how do you write x in terms of r and theta? R cosine theta. Well, r is t squared, and theta is t. So this becomes t squared cosine t. Y is r sine theta. Well, that would become t squared sine of t. Now z, how do you rewrite z? Yeah, the answer is z, which is 26t minus 6t to the 6. So this was just adding sort of an extra layer, saying, oh, I just need the first step is change my parametrized curve from one coordinate system to a different coordinate system. In particular, the coordinate system which works great for straight lines. So the Cartesian coordinate system is built for straight lines. It loves straight things. Now that we have that, then it's not so bad. So what do we need to know? Well, we need to know our point on our tangent line. So how do you find that? Right, you plug in t equals 1. And we're going to end up with cosine of 1, sine of 1, and then we're going to get 26 minus 6, which is 20. We also need our vector. Well, for that, we take our derivatives, x of t, x prime of t, y prime of t, z prime of t. Okay, so derivative of x prime, so that would be product rule. So 2t cosine t minus t squared sine of t. Derivative of y prime, 2t sine of t minus t squared, plus t squared cosine of t. And z prime, 26 minus 36t to the 5th. All right, we take our derivatives. What's next? Plug in 1, because we need to have the direction of our derivative there. So our vector for our line, well, that's going to be 2 cosine of 1 minus sine of 1, comma, then 2 sine of 1 plus cosine of 1, comma, and 26 minus 36 is negative 10. So our tangent line has the following form. It's going to be x, y, z. I plug in my points, cosine 1, sine of 1, and 20, then plus some multiple, and I'm going to just choose s, because I already have t involved in this problem. If I already have t as a parameter, I want to introduce a different parameter for my line. So I'm going to have s times the x prime at 1, 2 cosine 1 minus sine of 1, plus s times 2 sine of 1 plus cosine of 1, and then plus s times negative 10. So there's my tangent line at time 1. Now I want to know when it hits the xy plane. What's true about points on the xy plane? Z equals 0. Yeah, this is secret code for saying z equals 0, which means I come down here and I say, all right, set z equal to 0. That says that 20 minus 10s has to equal 0. So what does that say about s? S is 2. Now, we're almost done. This is not our answer. That actually tells us how long it takes. So it says that if our time, for example, was in seconds, that would say we take another 2 seconds. We don't know what time is being measured in this problem. So to finish up, we plug in 2. So our location, our x value, is at cosine of 1 plus 2 times 2 cosine of 1 minus sine of 1. And then the y-coordinate is at sine of 1 plus 2 times 2 sine of 1 plus cosine of 1. And the z-coordinate is 0. Now you can simplify that a little bit. That's 5 cosine of 1 minus 2 sine of 1. And then this would be 5 sine of 1 plus 2 cosine of 1 and 0. But that's about as simple as you can get. And therefore, that's our answer. That's where it's going to hit the xy plane. All right. Good. So these problems are very popular. There's another one that you should look at on a recent exam. It was about, I think it was 1 year ago, the rocket ship problem. That's another good one to look at. Okay. Well, changing gears. Let A, B, C, D be the 4 corners of a parallelogram with point C opposite from A. So let's see if we can figure this out. So we have a parallelogram. So we have point A, here's point B, here's point C, because it's the one opposite from A. But then remember, it's a parallelogram, so these sides are parallel. So we have a picture here, A, B, C, D. Given that we know some points, so we know that A, this is at the point 3, 1, negative 2. B, this is at the point 4, 1, 5. And that D, that's at the point 1, 4, 3. We need to find the location of C. And then there's a second part. So let's start by finishing this, determine the location of C. Well, how can we find C? What we can do is we say it's a parallelogram, which means the sides are parallel, but in particular we can represent the sides by vectors. So there's this vector that goes from A to B. So we find that vector by looking at the change. 3 to 4, that's a 1. 1 to 1 is 0. Negative 2 to 5, well, that's a big change, that's 7. Then up from A to D, that's also a vector. So 3 to 1, I went down by 2. 1 to 4, went up by 3. And negative 2 to 3, I changed by 5. So those vectors represent the 2 vectors joining A and B and A and D. But in a parallelogram, those vectors have to match what are the sides opposite, negative 2, 3, 5. And similarly up here, this has to be the vector 1, 0, 7. So now there's actually 2 choices as how to get our missing point C. Because the vector, that's how we change. And we're starting at a point, and if I know where I start and I know how much I change, I know where I end. So if I start at B, I could say, okay, I'm at 4, 1, 5. I'm going to change my x-coordinate by negative 2. Well, that says I better end up at 2. I'm going to change my y-coordinate by 3. So that's going to be a 4. And I'm going to change my z-coordinate by 5. So I better get 10. And therefore my point is 2, 4, 10. Now, I did that by going from B. I could have done it by starting from D as well. So if you start at 1, change your x by 1, you get 2. 4, change your y by 0, you get 4. And 3, change by 7, you get 10. So this is using our geometry. Okay, we know how things are parallel. So, okay, that's the first part of the problem. Then there's an also. So also, find the area of the parallelogram ABCD. So here, we're now getting into areas. So how did we learn about area so far in the course? Well, for us, when we see area, we think cross product. So anytime you see area, you should say, is there a cross product involved? And the reason we say that is the area of a parallelogram. So if I have two vectors, u and v, then the area here is the magnitude of u cross v. But maybe it's not a parallelogram, maybe it's a triangle. Then what do you do? Divide by 2, yeah. 1/2 u cross v. So if you see any problem that says find an area of a triangle or find an area of a parallelogram, you're like, aha, I know what to do. Pull out the cross product. Of course, you have to make sure you have vectors. You can also do volumes. So this is a volume of a parallelepiped. Now the hard thing about parallelepiped is just spelling the word. Parallelepiped. Close enough. All right, Google search. So what's that? Well, essentially it's a three-dimensional box that's been tilted. But you have your u, v, and w. So if you have your vectors, say u, v, w, then the easiest thing to do is you make a 3x3 matrix where you put the u in the first row, the v in the second row, and the w in the third row. And then you take what's the determinant. This is what we use to take the cross product. Take that determinant, take the absolute value, and this will find you the volume. So finding areas of parallelograms or finding volumes of parallelepipeds, if it's a volume of a flat thing, pull out, it's a cross product type relationship. This, by the way, is the same as w dot u cross v in absolute value. That might be how you remember it. As long as you remember something, you're good to go. So what do we do? Well, the good news is we've actually started because we found the vectors. So this is basically just a, do we remember how to take a cross product? So we do that. That's ijk 107, negative 2, 3, 5. Let's see, I times 0 times 5, that's 0i. J times 7 times minus 2 is minus 14j. K times 1 times 3, that's 3k. Going the other direction, minus 2, 0k, that's 0k. But we subtract it. 3 times 7 times I, 21i, subtract. And 5 times 1 times j, that's minus 5j. So it looks like we're getting negative 21, negative 19, and 3. Now, those are big numbers. It makes me nervous. But I don't have to be nervous because I can just check. Negative 21 plus 0 plus 21. All right, good, that worked. Negative 42 minus 57. All right, that's positive 42, minus minus. Then there's negative 57 and plus 15. Okay, 0, good, good. So what's our answer? Well, the answer is, this is the square root of negative 21 squared plus negative 19 squared plus 3 squared. And what do we do? Yeah, leave it like that. It's good enough. There you go. There you go. Now, it might be the case that we give you nicer numbers, but if they're not nice, you just leave it like it is. Okay. Find the osculating plane to the curve r of t at time t equals 0. Recall that the osculating plane contains the point on the curve, the direction of velocity, and the direction of acceleration. So that's pretty good. In fact, they've given away a lot of information to us. We know that we're looking for a plane. So whenever we're looking for a plane, what do we think to look for? a point in the direction, in this case the normal vector. Okay, and it even tells us how to define these things. It says, hey, the point on the curve has to be a point in the plane. So we look at on our curve here, we know we're at time 0, so we plug in 0. When we plug in 0, we get the following. The point, which is r of 0, well, that's going to be 0 plus 2 plus 0, which is going to give us 0. And 1 plus 0, which is 1. And 0 plus 1, which is 1. So 0, 1, 1. Now, I know it's a vector right now, but the vector is a stand-in for the point. Okay, we are also told that the plane contains directions. So these two directions are inside the plane. So we should find those two directions. So r prime of t, take the derivative, we get secant squared of t plus 3t squared, and then 2t, and then we get cosine t minus sine t. And we'll do it for r double prime of t. So derivative of secant squared, that's 2 times secant of t times secant of t tangent of t. So we do chain rule, plus 6t, comma 2, comma negative sine of t minus cosine of t. So there's our velocity and our acceleration. Now we're after some vectors in the plane, so we need to evaluate these. So r prime of 0, 0, yes. We plug in and we see we get secant of 0, which is 1, plus 3 times 0. Well, that's 1. 2 times 0 is 0.
Point vector be 2, 1, 1, not 0, 1, 1.
Ah, you're right. Thank you. Should be 2, 1, 1. Good to double check. All right. I think the rest is true. Okay, so now you're making me nervous. 1 minus 0 is 1. Our double prime of 0, well, 2 times 1 times 1 times 0, plus 6 times 0. Okay, that's 0. And then 2, and minus 0, minus 1, minus 1. Now, these two are vectors in the plane. I don't want vectors in the plane. I want something perpendicular to the plane. What can I do? Cross product. So if I have two things in the plane, cross product gives me something perpendicular to the plane. So we're going to take their cross product. 1, 0, 1, cross 0, 2, negative 1. You're probably thinking, are we going to be doing a lot of cross products? You will do a non-trivial number of cross products at some point in this semester, probably as soon as the next exam. So let's see, we'll get 0i and 0j and 2k and 0k minus 2i plus j. So minus 2, 1, 2. But now you've made me second guess everything I do. So minus 2, 0, 2. That adds up to 0. That's good. Then we get 0 to minus 2, which adds to 0, which is good. So our normal vector is negative 2, 1, 2. We have our point, we have our normal, and therefore we can find the plane. Minus 2x plus y plus 2z, the coefficients coming from the normal vector, is equal to, now we plug in 2, 1, 1, minus 4 plus 1 plus 2, negative 1. Minus 4 plus 1 plus 2. And that's the answer. All right. Good. Good. All right. Number 8. Find the point on the line x equals 2 plus t, y equals 3 minus 2t, and z equals 3t, closest to the point 10, negative 1, and 4/9. So this is a problem that we're after a point on the line. So what should we think of? Now there's a couple of ways to do this one, but here's the way I like to think about it. I have this line sitting out here in space. Here we go. That's x equals 2 plus t, y equals 3 minus 2t, z equals 3t. And then somewhere I have this point, 10, negative 1, 4/9. I want to find, there's some point on this line which is nearest to that point that we're after. And I want to figure out which point that is. So the intuition says the following. The intuition says if I were to drop straight towards that line, to that nearest point, this is the point I'm after, this point right there, that I'd be perpendicular. Now, unfortunately, it's not so clear how to get to that right away. But we can use sort of this notion. We say, okay, let's think about what's true. So one of the things that's nice is we know our setting. We know we're in a three-dimensional space. And so we say, okay, what's perpendicular to a line in a three-dimensional space? A plane. So in 3D, if I want to be perpendicular to a line, I can think of that as being represented by a plane. So a plane gives a nice thing which captures a lot of perpendicular things all simultaneously. Conversely, suppose I want to be perpendicular to a plane. What can I look at? I can look at a line. So when you see problems of this, like find the nearest point, one of the things is you want to say, well, let me use this sort of perpendicular structure of space. So for us, we say, okay, we're given a line. What we're going to do is we're going to make a plane that's going to contain lots of perpendicular things, but also contain the one point that we want to be nearby. So our goal is to find a plane initially. So what's our plane? Well, it has to contain the point that we want to have be nearest. So we want to have it contain this point, 10, negative 1, 4/9. And the direction of this plane, which here I'm talking about the normal vector, well, what will that be? Well, it's perpendicular to the line, which means it's perpendicular to the direction of the line. So we read off the direction vector. What's our direction vector? 1, negative 2, 3. So 1, negative 2, 3. So now we write down our plane. X minus 2y plus 3z is equal to, well, do a little computation to the side here. X is our 10. Minus 2 times minus 1, that would be plus 2. And then plus 12/9. But of course, I really should have written that as 4/3. So let's see, that's 12 plus 4/3. And 12 is really 36/3. So that should be 40/3. Okay, so there's our plane. Now, how do we get the point? We look at the intersection. So the point here, this is our intersection of our plane and line. All right. So what do? The answer is we take this x, y, z and plug it into that relationship. So we have 2 plus t minus 2 times 3 minus 2t plus 3 times 3t should equal 40/3. So we start grouping here. We get 2 minus 6. That would be negative 4. Then plus t. Here we'll get plus 4t plus 9t. So t plus 4 plus 9t. Okay, so that should be 14t. That's equal to 40/3. So the negative 4 we can bring across as a plus 4. And plus 4 is really 12/3. So we get that, that's 52/3. So 14 times t is 52 divided by 3. What comes next? Divide by 14. And, it was supposed to be a nicer number than this. Well, this will teach me I should always double check my examples before I do them. Oh well, live and learn. Okay, all right. So t is 52 divided by 3 times 14? 42. Yeah. So you can cancel it too. So that's 26 over 21. So what do we end up with? Well, the answer is we plug t back into the line. So the point, the nearest point, would be 2 plus 26 over 21, comma 3 minus 2 times 26 over 21, comma 3 times 26 over 21. And that's fine. We can just leave it as that way. That's certainly a point you wouldn't have guessed. So it shows you, sometimes you need the math. You might think, I know what I'll do. I'll just keep guessing points because the answers are always nice. Not always. Not always. All right. Good. Find kappa, which is curvature for the curve r of t equals 2/3 t cubed, comma t squared. Simplify your answer as much as possible. Now, it's possible that some of you have not yet looked at curvature yet, since we're not going to talk about that till our next lecture. But I'm still going to talk about it now because it is a possible topic for the exam. So the important thing to note is that kappa is not so hard to compute. It turns out that kappa, you can write it as the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. So if you're familiar with the decomposition of acceleration, it looks a little bit like a sub n. In that, if you recall what a sub n is, that's a sub n divided by the magnitude of r prime squared. So how do you compute this? Well, really, the hard thing is just remembering the formula, and then you go through and do the computation. So for us, we'll have the formula here, because this is what it is. Check with me on Monday if you don't believe me. So r of t, 2/3 t cubed, t squared. We're going to need to have r prime and r double prime. R prime of t, what will that be? Okay, 2t squared and 1 and 2t. R double prime of t? 4t, 0, and 2. All right. Now from here, we just sort of look at what we need. Well, we need to find the magnitude of r prime. So we'll find that. So the magnitude of r prime, that's the square root of square each entry. So that'll be 4t to the fourth plus 1 plus 4t squared. And this is similar to one we had earlier, where if you rewrite the order, that's 2t squared plus 2 times 2t squared times 1 plus 1. So a lot of these problems will be the case that things just happen, 2t squared, things just happen to factor very nicely. So you should expect nice factorization to happen. So it turns out that the magnitude of r prime is 2t squared plus 1. All right, what else do we need? Well, we need to take this cross product. So r prime cross r double prime. So what is that? It's going to be I, j, k, and then r prime, 2t squared, 1, 2t, and r double prime, 4t, 0, 2. Now you might say, are we allowed to do that? Are we allowed to take cross product when we have variables in there? And the answer is yes. Yes, you are. It works just the same as any normal cross product does. All right, so I times 1 times 2, that's 2i, j times 2t times 4t, that's 8t squared j, k times 2t squared times 0 is 0k. Then we go in the other direction, 4t times 1 times k, that's minus 4tk. 0 times 2t times I, 0i. 2 times 2t squared times j, that's minus 4t squared j. 2, 4t squared minus 4t. Now, what should we do? we should check. And we should still have it be the case that the dot products are 0. So if they're not, something's wrong. 8t, 0, negative 8t. Okay, that all zeroes out. 4t squared plus 4t squared, that's 8t squared minus 8t squared. Good. So our cross product's okay. Then take the magnitude, r prime cross r double prime. So that's the square root of 4 plus 16t to the fourth plus 16t squared. Well, if you look at that, you can say, hey, if I just pull out a 4, this is really 4 times, and I'll just write it as 4t to the fourth plus 4t squared plus 1. Well, the square root of 4, I know that. That's 2. And this part, this other part, I say, hold on a second. I've already done that. That's the same thing I saw before. So I know what it's going to end up being. I can redo the steps, but it'll end up being 2t squared plus 1. So our final answer for curvature is that curvature is this r prime cross r double prime 2 times 2t squared plus 1 divided by the magnitude of r prime cubed, 2t squared plus 1 cubed, which of course you can simplify because you can cancel one of those 2t squared plus 1s. So you get 2 divided by 2t squared plus 1 squared. All right. I think that's as simple as we could possibly hope for. Now, at this point, you might be a little bit nervous and saying, that's non-trivial, and we're going to be tested on this in the very near future. The good news is that once you get the formula, it's really just a process. And once you have the process, it's not so bad. The other thing is we know that you haven't had much time to work with the the curvature. And therefore, any curvature problem we put on will be sufficiently simple that you'll be fine. We look out for our students. All right. So let u be the vector 1, negative 2, 2. Let r of t equal e to the 2t minus 2 sine squared of t minus 4, and comma, e to the t plus cosine squared of t plus t, comma, t minus 1. Find a formula for the projection of r of t onto u. And then there's some other stuff. So let's just do that first thing because it says find that formula. So this is a question about projection. So in general, the projection works really nicely. If I want to project a vector v onto a vector u, this would be u dot v over u dot u times the vector u. This vector that you end up with here, this is always a vector that you project onto. So we're projecting onto u, so we need to have it and pointing parallel to u. So it's some scalar multiple of u. And once you remember that, then you say the downstairs is going to be whatever vector we're projecting onto, and upstairs we have one of each. So that's the formula for projection. Now in our case, u is a pretty nice vector to work with. 1, negative 2, 2. So we can say a couple of things here. U dot u, well, that's 1, negative 2, 2, dot 1, negative 2, 2, which is 1 plus 4 plus 4, giving us 9. So there's u dot u. Now, how about u dot v? Well, in our case, we're going to have u dot r of t, because our vector v is this parametrized curve. So that's 1, negative 2, 2, dotted with e to the 2t minus 2 sine squared of t minus 4, comma, e to the t plus cosine squared of t plus t, comma, t minus 1. Well, let's hope things simplify. Okay, so we remember our dot products. We have 1 times the first entry. So e to the 2t minus 2 sine squared of t minus 4. Then minus 2 times the next entry. So I'll write that as minus 2 times e to the t plus cosine squared of t plus t. And then plus 2 times the last entry. So plus 2 times t minus 1. Now, this is a case that we see that there's this and here. And if we actually look at it, determine all the times when the projection is a zero vector, this is probably a case it's a good idea to simplify because we're going to do something with this projection. So if you're going to use it, your computation as a tool later on, you want it to be simple. If you're not going to use it as a tool, don't simplify. So what can we do to simplify? Let's just write it all out. That's e to the 2t minus 2 sine squared of t minus 4 minus 2e to the t. Remember, this minus 2 carries through. Minus 2 cosine squared of t minus 2t plus 2t minus 2. Does anything happen here? Sorry, what? The two t's cancel. That's good. Anything else? Yeah, the sine squared and the cosine squared. We must have lived a really good life because look at how nice things are happening. Things are falling into place. So the negative 2 sine squared, negative 2 cosine squared, that's going to become negative 2. But we also have a negative 4 and another negative 2. So we can actually combine all those pieces there together to produce minus 8. So u dot r of t, that's e to the 2t minus 2e to the t minus 8. So the answer for the first part of the question, the projection of r of t onto u is this thing, e to the 2t minus 2e to the t minus 8 over 9, because it's u dot v over u dot u, times the vector 1, negative 2, 2. All right, so that's the first part. That's part of our answer. The second part says, when is the projection the zero vector? Well, what's true about the zero vector? Sorry, what? Yeah, the zero vector has all entries 0. So how could I end up with having a zero vector? So the zero vector could happen, in order to get a zero vector when the term in front is equal to 0. So in other words, when I scale by 0, I get the zero vector. If I scale by something not 0, it's not the zero vector. So, in order to be 0, well, the over 9 doesn't matter. It's this numerator. I need to have e to the 2t minus 2e to the t minus 8 equals 0. Well, how do I solve that? So I can think of this as e to the t quantity squared minus 2e to the t minus 8 equals 0. And then we can have sort of a stand-in. We could say, let's introduce something called capital X for e to the t. Suppose you have capital X squared minus 2 capital X minus 8 equals 0. Well, what do? Well, we hope it factors. Does it factor? He asks us. He writes down in parentheses. It probably does. So let's see. We need to have two numbers multiplied negative 8, add to negative 2. So minus 4 and plus 2. Which says that this x has to either be 4, remember that e to the t is x, or it has to be negative 2. Okay, well, can we ever have e to the t be negative 2? No, e to the t can't be negative, so that's not possible. Therefore, it happens when e to the t equals 4, which happens if t equals natural log of 4. And that's the answer to the additional part of the question. So it's going to project to become the zero vector at time t equals natural log of 4. All right. Number 11. Find a sub t and a sub n. So this is a decomposition of acceleration problem. For our parametric curve, r of t is t plus t squared t minus t squared, and 2t. All right, well, there's two ways to do your decomposition problems. So option one is your algebra. In other words, we're going to use formulas. And option two is your geometry. So geometry, here I'm specifically referring to the dot product and the cross product. Now, when should you use them? Generally speaking, algebra is usually the fastest and most likely to not make a mistake if you have a magnitude r prime of t is simple. So if you get to the point where you say, oh, the magnitude of r prime of t is really clean, then algebra is great. If it's not, it gets messy. Geometry can sometimes actually be simpler. For instance, if you want your a sub t and a sub n at a particular point, it can be faster in some cases. But definitely, if our magnitude of r prime of t is simple, we're going to go with algebra. So let's just find out if that's happening in this case. So we have r of t, and it makes sense that we're going to have to look at r prime. We're going to have to look at r double prime eventually. So we have r of t, our position. I'll rewrite it here. So we have them all lined up, t plus t squared, t minus t squared, 2t. What's r prime of t? 1 plus 2t, 1 minus 2t, 2. Now, we'll pause for a moment. Magnitude of r prime of t, well, that would be the square root of 1 plus 2t squared plus 1 minus 2t squared plus 2 squared. Well, what does that turn out to be? So that's the square root of 1 plus, and we have 4t plus 4t squared plus, and here, 1 minus 4t plus 4t squared and plus 4. So those will cancel. 1 plus 1 plus 4. That will give us 6. 4t squared plus 4t squared. That's 8t squared. All right. Well, let's do it algebraically. It's not so bad. All right. So what is the algebra way to do it? So the algebra way to do it is to make the following two notes. First thing is to note that if I'm looking for the tangential part, that's our a sub t, how much of acceleration in the direction of motion, that's equal to the derivative of the magnitude of r prime. So, in our case, we can now answer that question. That's the derivative of 6 plus 8t squared to the 1/2 power. So we use the chain rule. That'll be 1/2, 6 plus 8t squared to the minus 1/2 times the derivative of the inside, which is 16t. And so you can clean that up a little bit. 1/2 times 16t, that will give you 8t. And then downstairs, you have this negative, so that's the square root of 6 plus 8t squared. Okay, so again, this is our a sub t. So we're halfway done. Now, how do you go and get the other half, your a sub n? Well, we keep going. We definitely need our second derivative. So r double prime. So what's our second derivative going to be? So 2, negative 2, 0. Now, the second part, when you're looking for a sub n, is you say, hey, the magnitude of r double prime squared, which is really the magnitude of acceleration squared, is the same as just if I add a sub t and I square that plus a sub n and I square that. Oh, whoops, sorry. I don't need the absolute values. This is just a sub t squared plus a sub n squared. Okay. These aren't vectors. These are numbers, scalars. So the nice thing is we have r double prime. So the magnitude of r double prime squared, well, that's going to be 2 squared plus negative 2 squared plus 0 squared, which will turn out to be 8. So we get that 8 is equal to 8t over the square root of 6 plus 8t squared plus a sub n squared. Because I have the magnitude of r double prime squared equals a sub t squared plus a sub n squared. Where do we go from here? Well, we rearrange. So a sub n squared will be 8. Then we're going to subtract off this expression. So subtract 64t squared over 6 plus 8t squared, which is what you get if you square that expression. What can we do to simplify? Well, we can get a common denominator. This common denominator would be 48 plus 64t squared over 6 plus 8t squared. That would happen, that's for the first term, when you get it over 6 plus 8t squared, minus 64t squared over 6 plus 8t squared. And we see when you put these together, you end up with 48 over 6 plus 8t squared. Now, this is not a sub n, it's a sub n squared, and therefore to finish up, take the square root. So we get that a sub n is the square root of 48 over 6 plus 8t squared. All right, so that's the algebra way to do it. So if you need to find acceleration, you say, all right, well, first off, find your derivative, find velocity, find the magnitude, take that derivative, that's a sub t. That's pretty quick. Once you have that, you basically pull out Pythagorean theorem, because it's Pythagorean theorem, and that gets you your missing side. Your missing side is a sub n. Okay, whew, good. Any questions on that one? All right, we're doing pretty well. We're going to make it. We're going to make it. Plenty of time. Now, find the centers and radii of both spheres which satisfy the following. So we have to have that the sphere is tangent to the plane 2x plus y minus 2z equals 7, and it's tangent to the plane 8x minus 4y plus z equals negative 24, and the center has to lie on a line x equals 2 plus t, y equals 3 plus 2t, and z equals minus 3t. Now, I think maybe the hard part about this is trying to figure out what's going on. So let's think about what's going on. So if you're not sure what's happening in 3 dimensions, think of 2 dimensions. So we say, okay, instead of spheres, instead of planes, we can think of 2 lines. So I have 2 lines. These represent my 2 planes. And then there's this other line that's going through space. And what am I looking for? I'm looking for a sphere. And what a sphere is representing is it's going to be a circle. And I want a sphere that has the following beautiful property. The center is going to be on the line, and it's going to be tangent to the planes. In other words, it would touch the lines here. So that's an example of what I'm after. So I want the center to be on the line that I'm given, and then if I put in that sphere, it's going to touch, just touch. So let's think about the basic geometry. Now, again, that's a 2D picture, but you can think, again, if you have a 3D picture about what's true. If I have a plane, and I have a sphere which just touches at a single point, what's true about the relationship between that sphere and that plane? Someone's mentioning the radius. What's true about the radius? Yeah, well, in particular, if you look at the radius of the sphere, and people are mentioning really great ideas, things like perpendicular, it's equal to the distance to the plane. So I'm going to just barely touch the plane if the center, and when I say the distance to the plane, I should be really explicit, the distance from the center of the sphere to the plane. So I'm going to just touch a sphere. In other words, remember that tangent means touch. If the distance is exactly the radius. So, what do we have here? Well, we know we need to be a certain distance away from the two planes. And the distance from one plane has to match the distance to the other plane. So, our idea. So to be tangent, you need to have that the distance to both planes must be equal. Now, when we say distance, well, what do we mean? Well, distance from our centers. So we should probably have a recall. So what's our formula for our distance to plane? So if I have a point x0, y0, z0, this is just an arbitrary point, and I have a plane ax plus by plus cz equals d. The distance between the point and the plane is given by the following formula. Namely, you take x0, y0, z0, and you start plugging in. So ax0 plus by0 plus cz0. But now you subtract d. So essentially you look at how far apart these two terms are, and that's almost it. The only thing you have to do is have to divide out by the square root of a squared plus b squared plus c squared. Because ABC is not unique, you might have some scaling term going on. So essentially, the distance between a point and a plane is more or less saying how close are these two sides of the formula. Is roughly what happens. Now we haven't done the distance formula, and you might say, are we expected to memorize the distance formula? Well, probably not. You can always just rederive it. I find it more useful to do the geometry, but from time to time there will come a problem. And I would say that if this were a real problem on an exam, we would give you the distance formula. It's already challenging enough if you didn't remember it. But on a review problem, well, we'll let you think about it for a little bit. Okay, so we're kind of in a good place. I know we haven't really done any computations yet, but we've done the hard part, which is we've thought about what's going on. So our goal is let's figure out where should our center be. And the way we're going to do that is we're going to look at the distance. So we're going to look at the distance to the centers. So here we go. X is 2 plus t, y is 3 plus 2t, and z is minus 3t. So let's start with the 2x plus y minus 2z equals 7. So that distance there is going to be 2 times 2 plus t plus 3 plus 2t minus 2 times minus 3t. And then I'm going to subtract 7. And I'm going to divide that by the square root of 2 squared plus 1 squared plus negative 2 squared. So this is the distance from an arbitrary point on my line to the first plane. That has to be the same as the distance from that point, arbitrary point on the line. So 8 times 2 plus t minus 4 times 3 plus 2t plus minus 3t. So again, I'm plugging in x, y, z. And then minus minus 24 makes plus 24. Divide that by the square root of 64 plus 16 plus 1. Because I have 8 squared, negative 4 squared, and 1 squared. Okay. Any t where this is true, that's going to work. Because that's going to be a point on the line which has the same distance away from the two planes. And by the way, this number, whatever it turns out to be, that's our radius. Because that's the distance. All right. There's not a lot of space left on this paper, so hopefully the rest of the problem is very short. So let's see what happens. Let's simplify this numerator. We get 2 times 2, which is 4. We get a plus 3, which is 7. Then we have a minus 7, which means the constants all cancel. Then we're going to get a 2t plus another 2t plus 6t, which means that upstairs we have 10t, absolute value. Then downstairs we have square root of 4 plus 1 plus 4, that's square root of 9, which is 3. Which, of course, we could pull the 10 out. So this is 10/3 absolute value of t. Okay, that's got to be equal to, on this side, what happens? Well, we have 16 minus 12, so that's 4, plus 24. So that makes what, 28? Am I doing this right? 16 minus 12 plus 24? Okay. All right. I suspect I'm going to have terrible answers, but oh well, always should check before you do the problem. Okay. 8t minus 8t minus 3t. So the 8t and the minus 8t cancel. We're left with minus 3t. And then downstairs, we're left with 64 plus 16 plus 1 is 9. Okay, I can tell I made a small mistake. Can I change this ever so slightly? Don't tell anybody I changed it. We'll edit it so I didn't make the mistake. We're going to change this minus 24 to minus 23. There we go. No one has to know. Don't tell anybody. If we make it 23, instead of 28, what do you have? 27. Yeah, that sounds a lot easier. Because notice, what can you do? Look, these both have factors of 3. So you can pull out the 3. So, all right. Hey, that's fantastic. Okay, so that's 9 minus t, absolute value, times 3 over 9. Or if you like, absolute value of 9 minus t over 3. Someone wants to ask, can we do that kind of on the test? Just change it? No, because on the test we checked it better. It's been more heavily vetted. All right, so moral is, what do we need? We need 10 times the absolute value of t be equal to, and because it's absolute value, it doesn't really matter which order I take it, it's absolute value of t minus 9. So that's what I'm looking for, is when is that true? When does 10 times the absolute value of t equal the absolute value of t minus 9? If I can find such a point, life is good. So how do I solve these things? Because these are absolute values, so we can't just be like, well, you know. So what we do is we check for the cases. Because absolute value can be messy. We say, all right, so there's a couple of possibilities. Because absolute value, this is going to switch signs at 0. Here, this will switch signs at 9. So what I want to do is I want to say, well, if I'm below 0, if I'm between 0 and 9, or if I'm above 9. So if I'm below 0, let me move this up. If I'm below 0, okay, I'm really going to run short on space here. Below 0, the left-hand side becomes minus 10t. The right-hand side becomes minus t minus 9, because both terms will be negative if I'm less than 0 initially. And so I have to put a negative in front. So what does that tell me? Well, that tells me that 10t equals t minus 9. Or that says that if I subtract t, 9t equals negative 9. So what should t be? So t should be negative 1. So there's one solution is negative 1. That's one solution. And you can check. Negative 1 absolute value is 1 times 10 is 10. Negative 1 minus 9 absolute value, that's going to be 10 again. Okay, suppose I'm between 0 and 9. What's the sign of this 10 absolute value of t? It's positive. How about this sign of t minus 9? It's negative. So I'd get 10t equals minus t plus 9, because I've got to switch the sign. Well, that tells me here that 11t has to equal 9, which tells me that t has to equal 9 over 11. So that's another solution, 9 over 11. Finally, suppose I'm bigger than 9. What do I get? Well, if I'm bigger than 9, both things are positive. So I get 10t has to equal t minus 9. 9t has to equal negative 9, which says t equals negative 1. But negative 1 is not above 9, so I ignore that. So we're basically done. We can actually write down our answers now. So here we go. Here are the answers. If we can fit them in. So the center and the radii. So to find the centers, for example, I plug in t equals negative 1 into where? Into the line. So the center, we solve for where they occur. So 2 plus negative 1 would be 1. 3 plus 2 times negative 1 would be 1. And negative 1 times negative 3 would be 3. How do you get the radii? Well, that's over here. It's 10/3 times the absolute value of t. So this radii is 10/3. Now to get our other center, we plug in 9 over 11. So 2 plus 9 over 11, well, that would be 31 over 11. 3 plus 18 over 11, that would be, I think, 51 over 11. That's a 5. 33 plus 18 is 51. And then we would get negative 27 over 11 is our last entry. And what's the radii? Well, it's 10 over 3 times 9 over 11. So the 3's actually divide through, and we get a radii here of 30 over 11. And there we go. So there's our center and our radii. See, we fit on one page. Good, good. This is a fun problem. It really pushes the geometrical aspects. All right, 3 more problems to go. So, given the velocity of a particle is given by e to the t plus 2t, 3t squared plus 1, and 2 cosine 2t at time t equals 0, and that at time t equals 0, the particle is at position 2, 0, negative 1. Determine the position of the particle at time t equals 2. So we're given v of t, the velocity. So velocity has been given to us. We're after something about position. See, it says determine the position. What's the relationship between velocity and position? Well, velocity is the derivative of position. So if I want to get to the position function, we would integrate. We essentially have the derivative. So integrate term by term. Integral of e to the 2t plus 2t, that's e to the t plus t squared plus some constant. Go to the next term, t cubed plus t plus some constant. And go to the last term, that would be sine of 2t plus some other constant. Now, we have to figure out what our constants are because we can't just plug in 2 and get our answer, because right now our answer has these unknown things in it, c, d, and e. If we plugged in 2 and said this is the answer, you're basically saying we don't know the answer. So we're going to plug in some information, and we're going to use the information given to us. So this is a problem where we have some initial conditions. Because it's a velocity problem, they gave us just enough initial conditions. We just need to know one thing about position. If it had been an acceleration, they'd have to give us more information because we would have had to do this twice. That would be twice as much fun. All right, so we plug in 0. R of 0, well, that would be 1 plus c, and then d and e. 0 is a nice number. We always like working with 0. So that should be 2, 0, and negative 1, which means that we can solve. So we get that c needs to be 1, d needs to be 0, and e needs to be negative 1. So updating, we can now say that our position function, that has the form e to the t plus t squared plus 1, because we have c equals 1, comma, t cubed plus t, because d equals 0, and sine of 2t minus 1. So how do we finish? Well, we need to know what happens at time 2. So the answer is we plug in 2. So we'll get e to the 2 plus 2 squared plus 1, which is plus 5. 2 cubed, which is 8, plus 2, which is 10. 2 times 2 is 4, so sine of 4 minus 1. And then we're done. Now I know what you're thinking. I would prefer this problem over finding the two spheres problem. Yes. All right. Number 14. The curves R1 of t, which is 5t plus 2, comma, log of t, comma, square root of 4 minus 2t minus t squared, and R2 of s, which is 7 root 2 times s to 3 halves minus 4, and e to the s squared minus 2s, intersect at a point. Find cosine theta, where theta is the angle of intersection. Now, the angle of intersection is the angle between their respective tangent lines. Okay, so first off, we're told that I have two curves which intersect at a point. Well, I need to figure out where do they intersect. So let's see if we can figure that out. So how do I know when two curves intersect? When their coordinates line up. So I have a bunch of coordinates here. So I have 5t plus 2, that's my x coordinate. That's got to equal 7. I have the log of t. That's got to equal the square root of 2, s to the 3 halves minus 4. And then I have this crazy expression, square root of 4 minus 2t minus 2t squared. That's got to equal e to the s squared minus 2s. In general, if I want to check if two things intersect, what I do is I say, okay, set the x's equal, set the y's equal, set the z's equal, and then solve. Now, in our case, I see one equation that's very tempting to work with. This first equation looks really good right now. So we're going to use that first equation. This would say that 5t equals 5, or t equals 1. Well, okay, so if I plug in 1, that says, I think the point should be 7, comma, and then log of 1 is 0, comma. Then I'd have 4 minus 2 minus 1 is 1. All right. Is that the point of intersection? Well, if we know they intersect, that's the right point. If we didn't know they'd intersect, what would we need to do? If we didn't know they'd intersect, we'd have to come to the other curve and say, well, what's the right choice? And we have to find a good number to work with. We say, okay, well, let's think. Let's actually figure out what S is, because we will need to know what S is at some point. We know where we need to end up at. So we have the last two equations to work with. Which one looks the best? Because remember now, we can actually update this. This one says this has to equal 0, and this has to equal 1, because we found the point 7, 0, 1. The middle one? We can try the middle one. That's okay, root 2's. If you like root 2's, that's cool. So this would say root 2 s to the 3 halves has to equal 4. Now, this is actually, if you look on this side, this is square root of 2. And this is really kind of a square root here, because there's a 1/2. So you can think of this as the square root of 2 times s cubed has to equal 4. Well, let's get rid of the square root. How can I do that? Square both sides. So that would say 2 s cubed is equal to 16. S cubed better be 8. So s should be 2. All right. So here we saw this is at t equals 1. Now, let's plug in s equals 2. We'll get 7. No surprise. 2 to the 3 halves. Well, that's really 2 times square root of 2 times square root of 2 times square root of 2, which becomes times another square root of 2 makes this 4. Minus 4 is 0. And then we have e to the power 2 squared minus 2 times 2. That's e to the power 0, which is 1. So yes, it does work. S equals 2. Okay, so now we know for sure that they intersect. We know when they intersect. But we're not done yet because that's when we were asked to find. We were asked to find the angle between the intersections. So to do that, we need the tangent lines. And really we care about the angle between tangent lines, which means we need the angle between their vectors of the tangent lines. How do we get those direction vectors for tangent lines? So direction vectors for tangent lines come from derivatives. So we get to take the derivative of both these curves. And the nice thing is, this is just like Calc 1. And the really nice thing is, we just get to do it 3 times as often, because once for each entry. So we just go through, no surprises. The first one will be 5, then we'll get 1 over t, and then we're going to get 1 half 4 minus 2t minus t squared to the minus 1 half times minus 2 minus 2t. I'm just applying the chain rule here. And the second, r2 prime of s. Well, the derivative is 0. And then the next term will be square root of 2 times 3 halves times s to the 1 half. And then comma e to the power s squared minus 2s times 2s minus 2. Okay, so there's our 2 derivatives. And we're going to plug them in at the right points. The right points are when we get to that intersection. So r1 prime at 1. So that would be 5, comma 1. And now we have to work this through. So 4 minus 2 minus 1. Well, that's good. That's just 1. 1 to any power is 1. We have minus 2 is minus 4. And then we have a half. So it's a half times 1 times minus 4, which means minus 2. R2 prime, we plug in 2, because our intersection's at 2. We're going to get 0. Then we're going to get square root of 2 times 3 halves times square root of 2. Well, square root of 2 and square root of 2 make 2. Divided by 2, that goes away. We're left with 3. The last entry, we're going to e to the power 4 minus 4. That's e to the 0, which is 1. Then we're going to get 2 times 2 minus 2. That's 4 minus 2, which is 2. So this problem has been reduced to saying, what's cosine theta for these vectors? That's where we're at. We found the intersection of these two lines, these two parametric curves, and we said, all right, what's the direction vectors? Those are the direction vectors, and we need cosine theta. Now, when you're looking for cosine theta, what do? What's our tool? We use dot products. Cosine theta is u dot v over magnitude of u, magnitude of v. So if I have two vectors, I can find cosine of the angle between them by that formula. So in our numerator, we take the dot product of these two vectors, 5 times 0, and plus 1 times 3, and plus negative 2 times 2. So 0 plus 3 minus 4. Downstairs we get the square root of 25 plus 1 plus 4. This is 5 squared, 1 squared, negative 2 squared. And then square root of 0 plus 9 plus 4. So we can maybe do a little tiny bit of simplification. Negative 1 over square root of 30 times square root of 13. But that's as far as we need to go, because we're looking for cosine theta, not for theta. And so that's the answer. All right. We've made it to our last problem. So, shown below are slices of a quadric surface taken at a few different values of y. Use this to identify the type of quadric surface and circle your answer from the following list. So we sort of are trying to say, okay, what's going on here? We see circles, and what we have is we have circles that are bigger, they're shrinking, and then they're growing big again. So the question is, what type of surface allows that? So there's a couple of surfaces. We should be familiar with these. The ellipsoid when you think ellipsoid, think of a sphere. So an ellipsoid, that should look very sphere-like. So it's possible that you'll see circles, but what you'll see is when you move through it, you'll see that we sort of start small, get big, get small again, and then they disappear. So it's not following this pattern here. The hyperboloid of one sheet, I should choose a different color here. This, sometimes you might call this an hourglass figure, because if you've ever seen what an hourglass looks like, it has sort of a similar shape. And so it looks something like this. And, well, that's promising. Now you might say, well, wait a second, that's the wrong orientation, right? Well, but there's other ways you can do this. So this formula right here, this would be if you had x squared plus y squared equals 1 plus z squared. But if you permute the variables, you're tilting it around. So this could be an hourglass, because you can see it's getting bigger, narrowing, and getting bigger again. So it's definitely a candidate. I suppose for completion, I should have pointed out that for a sphere, you get x squared plus y squared plus z squared equals 1. That's the kind of thing you get for a sphere. All right. Let's just go ahead and just quick reminder. Hyperboloid of two sheets. I don't think there's a good name for this one. What it looks like is you sort of have like two reflectors pointing away from each other. So they're not very good at communication. And this is x squared plus y squared equals negative 1 plus z squared. Or if you like, z squared minus 1. Definitely not right, because for this one, we wouldn't see anything in the middle, but we see something in the middle. A cone, do we know what that looks like? Well, cone looks like that. And that formula for there is your basic formula is x squared plus y squared equals z squared. Now, here, that's actually another candidate, right? Because if you look, you get big circles, smaller circles, then big circles again. Now, so how do we distinguish between a cone versus hyperboloid of two sheets? Well, if you look, they're pretty flat. So in other words, if you look along the sides of your circles, they go down at a constant rate. So if you were to sort of like put a line here, that's roughly how the circles should go. They should follow along the line, you know, the edge of this line. If you look, it's not following along the edge. So this is not a cone. How about an elliptic paraboloid? What does that look like? We have a nice name for that. We call this the bowl. And that's z equals x squared plus y squared. And it's a nice shape. That looks like that. All right. And the hyperbolic paraboloid, the last one. Do you know the name for that one? The saddle. Good. Now, what does that one look like? Well, that one is the hardest one to draw, so I sort of cheat and say it looks something like that. So that's a hyperbolic paraboloid. In one direction, you have sort of a parabola going up and down, up. The other direction, it's a parabola going down. So yeah, so that's what a hyperbolic paraboloid looks like. We don't see circles when we take cross sections. Okay, well, so we can see. Here are our different quadric surfaces, and we should be able to recognize some basic facts about them. So, what's ours? A hyperboloid of one sheet. That's the one we're after. We have that nice hourglass shape. All right, well, those were our 15 problems. Took us less than 2 hours. And you only have to do 7. Plenty of time, plenty of time.